So my project is on the mathematics of gerrymandering, in particular ways that we might quantify and describe ways that gerrymandering might occur, both in a real state and in a more generic sense. Now, as we just discussed previously, what we want to do in this kind of project is we're going to try to find all the different ways we can rearrange the congressional districts of the state and then see how all those different results compared to the actual election results to see if there's any discrepancies in place or anything along those lines. Now, let's actually go and discuss what gerrymandering is in particular. Gerrymandering is the manipulation of congressional districts in order to favor one political party. There are two primary ways in which we usually describe gerrymandering. There is packing, and that's where you take an opposing political party, place them as condensed as you can into one particular region so that their votes are only guaranteed in one section and you get the remaining districts. The other method, cracking, is where you try to split the difference of every opposing political party in such a way that you can guarantee that your side still has majority vote in that district. So we're going to try to explore the different ways that these two actions may occur. Congressional districts in general, you want them to be connected and compact. You want each of them to have approximately the same population size, and we want to avoid splitting counties when possible. It's okay to split it 2 or 3 ways, but we try to not do more than that. And I believe polynomials are a good approach for how we can actually resolve that issue with congressional districting. Polynomials are shapes where you have equally sized squares connected together by their edges. Our example is going to use trinomials, which are polynomials of 3 square sizes. So it could be horizontal, vertical, or L-shaped. Now, our methodology in approaching this gerrymandering problem is as follows. What we want to do is map a state to a grid where each section of the grid has near equal population size. So it's not by area rather than population. Once we have it all mapped there, we want to find all the different ways we can take our chosen polynomial shape and highlight. From there, we want to look at all the districts that we generate for our sample size and find the averages for each of these using a real election results. From there, we compare the true results to that of our sample space to see if any discrepancies are found. In the case of a 3x5 grid, what we can find is that there are 62 different ways we can partition it using the trinomial shapes. Those different shapes shown on the image on the right. So for our proof of concept, we're going to be using Oregon as part of our example here. So what I did was I took the state of Oregon and I put it into 15 equally populated sections. You'll notice that it's not all one-to-one with the actual area of the state. We're just doing it by population instead. From here, I chose the 2016 election results. And in each of these grids that you see down here, we have the votes in favor of Democrats for each region. So from that previous slide, we saw that Oregon was mapped to the grid, and each of those mappings are represented here by the percent vote for Democrats. Using those results from the 2016 election, I went to the sample space of 62 grids that we generated previously, and all the different outcomes are shown on the right here. 2 examples from the extreme ends are found on the bottom left. The leftmost map represents a districting in favor of Democrats, so one of the 5 blue maps that you see there. The image on the right represents a mapping in favor of Republicans, so one of the ones showing 3 Republicans, 2 Democrats. So you're able to take your grids and remap them back to the state to see what those partitions end up looking like when applied to your state again. Now, there are some visual indicators of packing or cracking that can occur from your gerrymandering maps. For example, packing is best exemplified by these examples here. Everything that was highly Democrat can be found in the top center of the grid maps. So by putting all of them together like so, we're able to pack all the Democrat votes into 2 regions, leaving the remaining 3 sections to be Republican votes. So this is a way for, despite it being a majority Democrat state, they were able to ensure 3 representatives from Republicans. Now, this example of cracking is actually in favor of Democrats. In this case, you'll find that most of the maps that we had in our 62-size sample space had the bottom right corner being in favor of Republicans. However, By using a section from the top center that was heavily Democrat and adding that to the Republican zone, we're able to crack it in such a way that it ended up falling to a Democrat representation. Now, this box plot represents when you take all of your sample space of 62 votes and you put it into an order of least to most Democratic, you're able to see the total different ways that these outcomes can go for each region. The box plots, whenever they are below the dotted line, represent a victory in favor of Republicans. Anything above the dotted line represents a victory in favor of Democrats. The points that you see marked here are the actual true results from the 2016 election. So as you can see in the 2016 election, it was 1 Republican and 4 Democrat votes. And you can see that generally follows the trend lines, though there are some discrepancies in place. It seems that the true votes actually ended up being fairly packed for the Republicans on the least Democrat region. So I thought that was pretty interesting. Adjusting the total state votes, if we were to lower the Democrat votes from 56% down to 51%, you'll notice that in general, it should play out that you have 3 Republican votes based on the current congressional districting, and the averages move down as well. Lowering it further, you'll see that there's now possibilities for the event of having 5 Republican representatives, and there's no cases possible for there to be more than 2 Democrat representatives. Now, we can generalize this. Our previous problems were more defined when using a 3x5 grid for the state of Oregon. However, we can take our ideas and put it into a more generalized form, for example, using a 3x n grid. A directed graph is one way that we can do so. A directed graph allows us to look at each possible way that we take our tiling and let each vertex represent the action where we map from one possibility to the next. And the vertex can only connect in cases where one movement can relates to the other. If we use the end state approach, here are the 10 different end states you can have if you're using trinomials. Now, the notation 0, 0, 0, that means that from that dotted line, nothing extends beyond that point. And we go from a top-down order when we describe this. So for 0, 1, 2, that means there's nothing extending beyond the dotted line of the first region. You extend 1 from the second, and you extend 2 from the third. We then take these different states, and then we look at all the possible ways that they can extend from there. So if it is possible to move from one state to the other, we use the arrow to notate that it is possible movement from that point. Since there's only a finite number of ways we can rearrange the grid, your directed graph is able to terminate, and it looks like so. We then create an agency matrix where 1 represents a possible movement, 0 otherwise. Using the transfer matrix method, we can describe our matrix T, where taking it to a particular power represents that grid size's possibilities for whichever entry that we choose. We're going to use the 0, 0 entry because we want our graph to begin and ends at a terminating straight line. So what we can also do is further describe the behavior of our graph by developing polynomials of our graph. So instead of just using ones to represent a possible movement, we're going to place a variable at each possible location. If we look at the top left, the 0, 0 entry, 0, 0, 0 is able to return to itself in the placement of a horizontal bar like we see in the variable W. So we place the appropriate variable into each region to show what tile causes that action to occur. Taking this variable to taking this matrix to the 5th power, you see the polynomial shown right down here. Now, what this tells us is all the different ways that we can range our grid. And if we were to plug 1 into every variable, you'd end up with 62, showing the sample size. If we were to look at, for example, our first polynomial here, 3d squared e squared w, that means there's 3 different ways that you can arrange 2 d tiles, 2 e tiles, and 1 w tile. So this gives us a good way of quickly generating our sample sizes, or sample spaces. So this project has several uses. It can be used in 2 diametrically opposed ways, really. One way is for us to find, detect, and prevent gerrymandering. And alternatively, a political party could use it in such a way that they'd be able to either overtly or subtly change election results in favor of their district. I know we're out of time at this point, but I could just continue by saying we can extend it further. For example, Florida has 27 districts. If we were to use a 3x(n) grid, a 3x27 grid would end up taking over 131 billion as a sample space. So while it can't really be done by hand, using technology, we'd be able to generate our sample space and use it for similar purposes. And there are some limitations when we look at polynomial tilings. It does show vertical placement, not horizontal placement. So when you're creating your sample space, you would still need to rearrange the tiles around in order to actually create your grid. Additionally, this is under the simplifying assumption that you only have Democrats and Republicans. If we're going to add a third or more political party, that might complicate things here. So in conclusion, this project's inspired by the work of Dr. Manley, but instead of generating randomly your sample space, I use polynomial tiling to do so. And this is a way that I think could be an intuitive and quicker way for one to generate those possibilities so that they can quickly determine gerrymandering. And this just goes over the references, acknowledgements, stuff like that. It does seem like I still need to cut it down a bit though. Yeah, it looks like I'm